The next part of Lecture 5 concerns quantum numbers. The solution to the Schrödinger equation resulted in 4 quantum numbers. This is a very complex polynomial, so therefore there are multiple solutions that work. The solutions to the Schrödinger equation give the probability region of each electron. This would be the general region an electron can be found orbiting around an atom. However, it's less like an orbit and more like a cloud. So we have n, the principal quantum number, L, the orbital angular momentum quantum number, m sub L, the magnetic orbital quantum number, and m sub S, the spin quantum number. Let's first start with n, the principal quantum number. This designates the level or shell the electron occupies. It is the primary indicator of the electron's energy, and it can have values 1, 2, 3, and upward. So this is the same idea as n from the Bohr model. The bigger the value of n, the further away the electron probability region is from the nucleus. The next quantum number is known as L, the orbital angular momentum quantum number. This designates the orbital shape and also gives us the number of nodes. It is a secondary indicator of the electron's energy. L can have values 0, 1, 2, upward to whatever n is minus 1. The L value is also given a letter designation. So this would be a good thing to memorize as it will be helpful in understanding electron configuration. Notice the S, the P, and those of you who are familiar with electron configuration also know there are D and F. So if an L value corresponds to 0, we use the letter S. An L value of 1, we use the letter P. L value of 2, we use the letter D. L value of 3, the letter F. 4, the letter G. And 5, the letter H. L is the value that adds the complexity that the Bohr model lacked. So if you are asked to give the quantum numbers for the 3D sublevel, n is the numeric value you see. The principal quantum number is 3. For D, recognize that the orbital angular momentum quantum number is 2. Remember that L gives us the number of nodes. So if you were asked how many nodes would be in a G sublevel, G corresponds to L equal 4. So that would be 4 nodes. What is the minimum value n must have for a G sublevel? Well, remember that L can be 0 up to the value of n minus 1. So if L is 4, n must be at least 5. The energy of orbital sublevels corresponds to n plus L. Remember that both n and L are indicators of the orbital's energy level and distance from the nucleus. So if you're asked which sublevel is higher in energy, just add up the numeric values for n and L. For 3p, n would be 3. P means that L corresponds to 1, so that would be 4. For 3D, n corresponds to 3. D corresponds to an L equal 2 value, so that would be 5. Clearly, 5 is greater than 4. So the 3D sublevel would be higher in energy and have an electron cloud, which allows the electron to be further away from the nucleus. Going back to the ideas of absorption and emission, if you have an electron that makes a transition from the 3D sublevel to the 3p sublevel, what will it be doing, absorbing or emitting? It's going from 3D, which corresponds to 5, to 3p, which corresponds to 4. That would be emission. Once you get to some of the outer orbitals, the suborbital that's higher in energy is a little bit more complex. So we're asked here to rank the sublevels in order of increasing energy, 3p, 3d, and 4s. And we're given this information. For a tie, the one with the higher n value wins. The n values are easy. They're the numeric value we see. So n would be 3, 3, or 4 for these sublevels. P corresponds to L equal 1, so that would be 4. D corresponds to L equal 2, so that would be 5. And S corresponds to L equals 0, so that would be 4. So clearly we can see that the 3D level is the highest in energy, but what do we do about 4 versus 4? Well, remember, the one with the higher n wins, meaning it is higher in energy. So our ranking should go like this: 3p, 4s, 3d. So perhaps you're a little confused why that overlap occurs, and with the term sublevel. The addition of sublevels is one way the Schrödinger model is different than the Bohr model of the atom. Remember, for the Bohr model, we had orbitals at n equal 1, 2, 3, and 4. The Schrödinger model is more complex. For n equal 1, there is only one level. For n equal 2, there are two sublevels. So that's what I mean by sublevels, the different orbitals underneath the principal quantum number value. So there is a 2a and a 2b, except we call them a 2s and a 2p. The third orbital level for the Schrödinger model is going to split into 3 levels, an A, B, and C, except we call those an S, P, and D. Now the Schrödinger and the Bohr model have something in common. The orbital gaps are going to get closer to one another as you go further from the nucleus. So can you imagine that when the third orbital level splits into 3 parts, and the fourth orbital sublevel splits into 4 parts, that there might be some overlap occurring? Let's zoom in. I hope it makes sense that we go 3s, 3p, 4s, 3d. And then there's more overlap occurring the further out one goes. So here's a question for you. For the transition 3p to 5p, select the value of n plus L and the type of transition. So of course one has to remember that if L is 0, 1, 2, 3, that we have designations S, P, D, and F. So we are, of course, speaking of P, so I believe you know what you need to do here. Take n plus L for each one, and then compare the numeric values. Here is 4D to 5P. So compare the n plus L values, and I want to remind you that when you have a tie, for example, 2 equal 2, the highest n has greater energy. So that will help you with this question. Let's move on to the next quantum number. This is m sub L, the magnetic orbital quantum number. This gives us the orientation of the orbitals of the sublevel, the orientation in 3-dimensional space. It also gives us the number of orbitals in a sublevel. M sub L can have integer values from positive L to negative L, including 0 in between. So if you're asked how many 5p orbitals are there, well, first remember that p numerically corresponds to 1. Therefore, M sub L can have values +1, 0, or -1. You see 3 values, so there are 3 5p orbitals. If you're asked how many 3d orbitals are there, remember that L corresponds numerically to 2. So the range of numbers from +2 to -2 gives you 5 orbitals in that group. So the L value starts to give us an idea of what these electron probability regions look like. If L equals 0, your number of nodes is 0. So the electron probability region of a 1s orbital is a sphere, and a 2s orbital is a sphere, but a larger sphere because we're now at a higher principal quantum number. And a 3s orbital is an even larger sphere. What about L equal 1? This means we're going to have one node. So imagine taking a balloon in your hand and pinching it down in the middle of the balloon so that you have a bulge on the top and a bulge on the bottom. That's what a p orbital looks like. Your pinching is the node. And remember that M sub L gives us orientation in space. These orbitals hold electrons. Electrons are the same charge, so they repel one another. So the only way to have them associated with the nucleus of the atom, which is in the middle here, is to have them orthogonal. So there is a px, a py, and a pz. The 3pz orbital is exactly the same shape. It's just larger. And where is our node? Where we have pinched down the center of the balloon. How about 3d orbitals? Well, remember that L numerically is 2, so there will be 2 nodes. And as far as how many of them there are and how they're oriented in space, remember that M sub L can range from +2 to -2. So there are 5 orbitals in this set, and each of those orbitals has 2 nodes. And here's what they look like. Remember that the nucleus is going to be in the center, so one electron region is like a cloverleaf in the plane of the screen. Another one is like a cloverleaf but coming out and going into the screen. And I trust you see how these do not overlap. There are 2 nodes, so notice that it cuts this into 4 regions. The last orbital, the dz squared, is kind of like our pinched balloon with a donut around it. And I know this looks very unusual, but it does have 2 nodes, and there is experimental evidence to suggest that these are indeed the electron probability regions. Every semester, someone asks me, what do the f orbitals look like? I'm sorry, I just cannot draw those in PowerPoint, so I had to take a picture from elsewhere. If L is equal to 3, then we're talking about orbitals with 3 nodes, and M sub L, which ranges from +3 to -3, gives us a set of 7. And here they are, your electron probability regions for the f orbitals. So here's a question for you. How many 5g orbitals are there, theoretically, according to the Schrödinger model? Let me help get you started on that. Remember that each L has a numeric designation. So if we go S, P, D, F, G, And we start 0, 1, 2, 3, 4. Now we have the L. As far as how many are in each set, you need to look at M sub L, which is going to range from plus L to minus L. However many values you have, that will help you determine how many 5G orbitals there are theoretically. If students would have a favorite quantum number, it would be this one, the M sub S. This is the spin quantum number. You can only have two values, plus 1/2 and minus 1/2. The way to describe this related to the Schrödinger model is what times itself equals 64. 8 is an answer, but so is minus 8. So think about the physics of how electricity is generated. Electricity is generated by spinning a magnet. Therefore, if you are moving an electron, won't you generate a magnetic field? That's exactly what this is. If the arrow points up, then north is up and south is down for that magnetic field. And if the arrow points down, then it is the opposite. We use these arrows to represent electrons. So in summary, N is your principal quantum number. It is the primary energy level indicator. It starts at 1 and goes upward in integers. L is your orbital angular momentum quantum number. It is a secondary energy level indicator, giving us the sublevels of the principal quantum number. It also indicates the number of nodes and therefore the shape of the orbitals. The restrictions for L is that it starts at 0 and ends at whatever n is minus 1. And of course you know that the numeric L values correspond to letters. M sub L is the magnetic orbital quantum number. This tells how many orbitals are in a sublevel and an indication of how they're oriented in three-dimensional space. The restrictions for M sub L are that it can be anywhere from positive L to minus L in integer values. M sub S is the spin quantum number. It indicates the electron's spin about its axis, whether it is up or down, and can have values plus 1/2 or minus 1/2. So here is a question for you. Using the rules for quantum numbers, select the set that is not allowed. Now, many times students go for answer B because we don't know what that element is. But if that element were to exist, and I'm sure it would be very radioactive and decay quickly, does it theoretically fit the restrictions on the quantum numbers? So try and find one where it's not acceptable. And as a hint, for this question, look at the relationship between L and M sub L. You're going to find a problem. Here's another set. One of these sets has an issue. And this time, please look at the agreement between N and L. So I am almost to the point of discussing electron configurations. I want to finish by going over the quantum numbers pattern. The lowest energy orbital has n equal to 1. If n is 1, L can only be 0, and M sub L can only be 0. The electron in this orbital can either have plus 1/2 or minus 1/2 spin. We call this orbital the 1s orbital. It's a sphere and it holds 2 electrons. For principal quantum number 2, L can be 0 or 1. Remember, the second principal quantum number has 2 sublevels. The first sublevel we call the 2s. It can hold 2 electrons, and it's a slightly bigger sphere. The next higher sublevel in energy, L is equal to 1, which means they come in a group of 3 for this sublevel. And for each value of m sub L, m sub s can have plus 1/2 or minus 1/2. So you notice these numbers offer different sets, 6 of them actually, to hold 6 electrons. We call this set of orbitals the 2p sublevel. All right, if the first level only has one level, and the second level splits into 2 sublevels, the third sublevel splits into 3 sublevels. So there is a 3s that holds 2 electrons. Now we have L equal to 1, so that gives us a 3p. And the combination of these values gives us holding space for 6 electrons. So there's a 3p set. And when L is equal to 2, we have a 3d set. M sub L gives us 5 potential orbitals, all at the same energy. Each one of them holds an electron either pointing upward in spin or downward in spin. So 5 times 2 gives us 10 electrons. And finally, the fourth principal quantum number has 4 sublevels. And now it starts to get a little bit crowded. But there are the 4s's, which hold 2 electrons, the 4p, which holds 6 electrons, the 4d, which hold 10 electrons, and the 4f, which I did not picture for you, but there are 7 of them, and 7 times 2 gives us 14 electrons. So please notice that whenever you have an s orbital, there will only be 1 in that level. Whenever you have P is like a bunch of 3 bananas. P's come in 3s, and they hold 6 electrons. And D's come in bunches of 5. And whether or not they are 3D or 4D, they hold 10 electrons. So that's a bigger bunch of bananas. Now I have these orbitals ranked on energy scale away from the nucleus. So the nucleus is down here. And instead of trying to draw the different orbital shapes, we can simplify this by using just boxes. So the closest orbital in the Schrödinger model is the 1s, followed by the 2s, 2p, 3s, 3p, and remember that exercise we had where the 4s tends to be lower in energy than the 3d, than the 4p, and I haven't mixed in the n equal 5. There are some that belong here, but this shows you the increasing n plus L values and the further distance of each of these orbitals from the nucleus. So if you were asked, what is the quantum number set for this particular electron? Well, we can see it's in the 2p sublevel. So 2, L corresponds to 1. I'm going to skip m sub L for a minute. It's pointing downward, so that's a minus 1/2. For m sub L can be plus 1, 0, or minus 1. Since we don't know what the axis is that this electron is oriented in, we could call this m sub L equals 0. But minus 1 would work, or plus 1 would work. You're allowed to use a range for m sub L. So in summary, historically, we've gone about 23 years from Thomson's plum pudding model to the Schrödinger model. And honestly, the Schrödinger model works best even today. There are physicists who work at refining this model, but in general it explains a good 95% of what we observe in atomic behavior, at least on the macro scale.